Hello everyone. My name is Scott Wright and I'm a senior consultant at One Spatial where I've been working for just over 5 years. I'm certified in FME Professional and FME Flow, and today I will walk you through the TfL road conflation case study and explaining how I used FME in the process. So just firstly, One Spatial, for those of you who don't know, is a leading global platinum partner of safe software and reseller of FME. And since 1999, we have worked closely with Safe Software as platinum partners to ensure you get the very best value out of your FME products. Okay, so just firstly, what do we mean by conflation of road networks? Conflation is the process of combining or integrating multiple road network datasets into a single unified dataset. Taking the best elements from each dataset, we can create a single source of spatial truth which improves accuracy, coverage, or detail by leveraging the strengths of different datasets. And the goal of conflation is to merge these datasets, combining the best aspects such as geometry, attributes, or metadata. So, what was the Transport for London challenge? In this instance, we had two sources of road data which we needed to conflate. The TfL1 model, which is historical and real-time data used by an internal modeling team to forecast potential incidents, and the Common Operational Road Network, also known as CORN, which utilizes the authoritative and detailed Ordnance Survey highways network to provide TfL with a high-quality source of information. And what were the TfL requirements? So with the CORN and the ONE model built using different geospatial networks and not linked out and not having linked identifiers, if you wanted to relate one to the other, you'd have to do this on the fly. So this has implications on the end performance of the system and can also impact the accuracy of the translation. So for the predictive component of the SITs to work effectively, TfL recognized that they had to address the problem of the misalignment of data sets, as there are key geospatial differences between them. And for One Spatial, what was our part? So One Spatial needed to devise a methodology and a process to incorporate all road layout examples and differences between both networks, and to define a rule set for relating the one network to the OS network using the tools available in FME desktop or form. And the goal for One Spatial and TfL was to realign a one model link to the OS highways master map geometry, and then to assign a TOID reference to each of the one model links. We would use linear references to define how far along the TOID the one model link's start and end point would be. And where a rule set couldn't be applied and therefore match a one network to an OS network, these would be flagged for the TfL manual updates. Okay, so what was our One Spatial solution? So this approach was to make a consecutive sweeps of the one network, applying targeted rule sets to identify matches between the one network road links and the OS road link. We would have rule application, which would start with logic that gives the highest match confidence, incrementally retaining the logic with further inference to find a match. The implication of this being that if this may be having a lower confidence but still conforms to a quantifiable logic. We had the expectation that there would be small sets of features remaining where any further transformation or inference would return insignificant results, and therefore manual intervention would be the most suitable course of action. So for our process, we kind of split the work into different methods, and the workspace has been designed to first identify a link between the OS master map and the one network using key attributes and geometric coincident matching. So basically, that was referring to the road name and the geometry. So the workspace first applies a large buffer of 15 meters to the one network features. And as you can see in these two examples, on the left, in the yellow, the Scion lane. So this is a road segment, and on the right, the same road segment, but with the 15-meter buffer. So as I was saying, within the workspace, we first buffered using a buffer of 15 meters. These features are then passed onto a line on area overlayer transformer. So with the highways data, this was used to create a list of toyed features which were contained within the one model buffer area. And also at this time, we would create the length attribute. Features which have an overlap with one model of the one model buffer feature are extracted and then tested to ascertain whether or not they shared the same name attribution as the highway overlap feature. There were instances where the two overlapping features did have road names, yet they didn't match, and so these were passed to a fuzzy matching criteria. So in this process, punctuation and symbols such as brackets, apostrophes, and dashes are removed, with the road network abbreviations as well, such as ST for street, YD for yard, RD for road. These would then be elaborated out. And then the data tested again to see if there was any matches on these new fuzzy logic name conventions. Once this was done, we aggregate the one model features and the highways, and we can calculate the total length of the one model feature which overlapped by the same highway road name feature, and the percentage coverage is calculated. So those features where we find cover over 90% and matching on a road name, we define this as having a high confidence level that we have found a toid for the one model feature. For those 90% or below 90%, we needed to move on to another method to try and interpret these. And this took the form, just for example's sake, with the fuzzy matching and the road name. Just in this example here, we can see the Ordnance Survey data within the same buffer as before. And then obviously with the percentage cover, so this is kind of showing the overlay of the Ordnance Survey over the top of the one model within the buffer. So as part of this process, we will be pulling out all of these sections of the Ordnance Survey data to relate the toid to where it touches the one model. So as I was saying, with features that were less than 90% coverage, we needed to have another approach to this, and this approach was the incremental buffer approach. So in this case, a smaller buffer of 0.05 meters is created on the one model features, which are passed obviously from the last features. As we can see in this example, this is just a one model line, and then pretty far zoomed in with this is the 0.05 meter buffer surrounding this. So again, within the workspace, we have our buffer of 0.05 coming through in the buffer. And then we're using the same line on area overlayer transformer approach. This is repeated again, and this will give us the list of toyed features that are within the one model buffer. We then take these features and they're filtered, and by having an overlap as well as having a length greater than 0.5. And also within this, we are taking into account the OS master map form of way attribute features. So within this, we're kind of looking at the traffic outlet link or a traffic link at a junction, these will be taken through as well. So again, features are aggregated, so we can get the total length of the one model feature which is overlapped by the same high-res feature. And again, we're doing our percentage coverage calculation. Those features which are found to cover over 90% of the one model feature are defined again as having a high confidence level. Just this example again, just to show you how, just visualize it, with our one model and our buffer, then with the same buffer but with our ordnance survey network. As you can see, just the difference there is an actual added road network to the bottom, unlike the one model, and then a combination just of all of those, just to see. I'll zoom in because this is just showing an example that they would never have matched based on a line-on-line overlayer. And this is why this approach was kind of needed, because they've obviously failed as one of them doesn't have a road name or doesn't match the road name to the other one. So this approach was needed. As we can see with this example, we can ascertain that they are with high confidence the same road. So again, as this is, we're incrementing the buffer logic within this. Those that were below the 90% coverage using the 0.05 buffer approach, we then pass this on to the next buffer of 0.25, and the same logic is applied with the resulting with those above 90% being filtered out, and then those below 90% are then again passed to the final buffer of an increased size of 1 meter. And then we're saying at this stage that the remaining features below this 90% are passed to the next method. So this next method was the no relationship approach. So this approach aimed to find features within the one model that had no relationship to any features within the high-res dataset. So we kind of realized at this point that the buffers had come to a point where we couldn't find any more without introducing error into the fact. And with that, we were trying to ascertain, it was like, why are these features not being able to be found? And from this, we kind of had the idea saying that, well, then they must not exist in one of the feature sets. So we sought to actually prove this point, and this point was proven when using the neighborhood finder approach. So within this, we're taking a maximum distance of 15 meters, and as this is used to find the highway features that were within 15-meter radius of the one model features. So features without any neighbors within 15 meters were classed as geometry only within the one model. And as you can see with the example on the right, in blue with the one model feature, and then in red with the highways data set, and we can see within the highways data set that that feature does not exist. There was also cases of where features found a neighbor within 15 meters, so one neighbor within 15 meters, but these had no previous percentage covers, and these were classed as features which did not exist in the highways network, yet their starting vertex connects to an existing feature. So any features which remained unmatched from the combination of all previous approaches are defined then as unmatchable. So possibly with future workspace improvements, we could look at these features to provide a more definitive reason as to why they could not find a higher confidence match. But currently these are passed then to the TfL team for a manual investigation. So the second part of the process, or of the workspace, that we had to ascertain the direction that the roads were flowing in. And so we had to calculate the feature direction, and features within the one data model are, are duplicated, yet they differ according to their start and end vertices. And therefore, as I was saying, the second section of the workspace was designed to take the toids associated with each object ID from the one model feature, and then to determine its direction according to its start and end vertices. So this is the part of the workspace that looks at this. So for this source at this point, this is basically the highways data but duplicated, and then for the direction of the vertices, it's applied with a suffix of A or B onto the toid. So say a road is running in two different directions, when we duplicate that, we'll provide the single toid will get a suffix of A, and then for the other direction, we'll get the suffix of B. So the workspace joins this geometry from this data set to the toid that was associated with each of the one model features that we originally found, and then they would get an A or B attributed to them. We then found that if we used an azimuth degree calculation, so this calculation, it would determine the compass direction of each feature. So this was applied to the AB data of the highways. We then buffered 25 meters on the highways AB data, and this was used to clip the one model features to the extent of its corresponding highways toid, and this created the different sections that we were after of the toids which make up the one model feature. The same logic was also applied to the clipped one model features, and then the difference between these two azimuth degree calculations was then found. So the lower result obtained in this instant, the difference, the different calculation inferred the correct object ID and then in turn the road direction. So the closer to zero for both and matching meant that they both were flowing in the same direction. So the features are then recategorized at this point and given um, a new confidence attribute based on the different result calculation. So those less than or equal to 20 obtained a high confidence. Those greater than 20 but less than 25 medium, greater than 25 and less than or equal to 30 low. And then a final step of this section would remove small segments that had made it through. So anything smaller than 0.1 meters were excluded. And then these features were passed out to the final file geodatabase non-spatial table called the toid lookup. So this is an example of the output of the toid lookup. And as I said, the toid lookup is a non-spatial output of the match one model to OS toid features. So each one ID can be duplicated as the table splits the one model features into the sections covered by the OS network. So as you can see in the first example of the one ID 3, there are 7 occurrences of it, but each obtains a different toid, a unique toid. Each section also has the start and end point along which it meets the toid and the length of each section. So this was good for us in the final stages when we tried to ascertain have we managed to find the total length of the source one model. So if we were to add up the section lengths for each one ID, unique one ID, did this equate to the original length of that one model feature? So as part of this as well, then we wanted to account for all one model source features, and therefore a section was dedicated within the workspace to account for every source one model feature and focus solely on those that weren't written into the TOID lookup file geodatabase. So this found that there were instances within the one model where corresponding geometry would match but not in the correct direction. So in this scenario, the one model feature was defined as unmatched, as there technically was no Ordnance Survey geometry that it could match on when we take direction into consideration. So yes, it may have matched on road name, but that wasn't enough. We needed to account for the direction, and if the direction wasn't matching, we then had to class this as unmatched. A similar scenario as well is identified features whereby they matched with a directionality of both directions. However, the one model match would be in the opposite direction to the Ordnance Survey feature it identified with before direction was considered. And also part of this section of the workspace, we kind of focused on from previous methods. So we filtered from previous methods features were either identified as only existing within the one model data set, therefore having no geometry to match within the or from the Ordnance Survey, or they had failed to actually find any sort of relationship based on all our previous methods. And from this, we produced an Excel summary report. So the TfL team could see an account for every feature. So the summary tab within this report provides statistics on the percentage coverage of one model features that have been matched, and this is categorized by our confidence attribute, and the overall percentage coverage was also documented within the summary tab. So if we look at the summary tab here, we can see that nearly 97% of high confidence was found from our methods. So that is basically saying that we have found 97% coverage of the one model network from this process, or we can account for it. In total, if we add up our medium and low confidence, we can nearly say that 98% is accounted for, which is pretty high. For the other tabs, the no directional geom tab, so this lists those one model features that were found to have no match within the highways features, as they only had one directional geometry to match on. And the last tab, these were one model features that were defined as unmatched, and these one model features would need manual validation to confirm the correct TOID association, or whether there actually is any corresponding geometry to match on. And as you can see within the filters of the three descriptions, it's either no geometry within the highways data, or no match was found in that specific direction, or it was unmatched from all the previous methods. So if we just summarize then, were all our goals met? So the methodology and process used the tools available and we were successful in defining a set of rules that fine-tuned the matching process to a high degree of confidence. And I believe this can be shown in the result of the Excel summary report, where we can say that we have found 98% coverage, or account for 98% coverage of the network. And we can say 97% of that with high confidence that we can have an associated TOID to that one model feature. And the one spatial lookup as well, and it incorporates linear referencing to determine how far along the TOID, the one model link start and end points should be. So as I showed in the TOID lookup, It has the X and Y points as well as the distance between those points. And again, this was used to find out the percentage coverage of the one model of what we had actually found. And then we can say that where a rule set cannot be applied, the workspace accounts for every source one model feature and providing a reasoning why. So again, as seen in the summary report, uh, we can account for whether or not we can say that it has no geometry, or there was geometry but we couldn't match it because there was no high-waist geometry in that particular direction, or as we've seen a very small amount of these, our process wasn't able to determine and so therefore needed manual interpretation. So a benefit of using the FME approach is that the workspace can then be reused for Ordnance Survey and one model updates. So if there was any updates or within the data, this could be run again and produce the output. It also can be used to enable future improvements. And with the work taking place offline, running this workspace meant that there was no downtime of the previous system during the development. And just a final note, just to say, it's always amazing to have feedback from the client, especially if it is positive. And just to see here from Jamie, who was the GS lead for TfL at the time, just say we thought that inevitably one team or the other was going to have to change their way of working to deliver the predictive elements of SITs. And then by bridging this gap between the processes, the solution enabled both our GIS and modeling expert to continue working in their own way. And that, for Jamie and TfL, was the real benefit. So just as a way to wrap up, if the content that you've heard here has been helpful and has inspired you to learn more about One Spatial's FME training opportunities, we do run regular training events in FME form and flow, the details of which you'll find in the webinar following up with the follow-up correspondence. We also have a monthly webinar series where you can pick up helpful tricks and tips, as well as learn about, as in this case, the case studies in innovative FME use. So yes, I would just like to thank you for taking the time to listen today, and I hope you found the webinar both interesting and valuable. And it's been a pleasure to share the insights from the TfL road conflation case study and demonstrate how FME can be leveraged in practical applications. If you have any further questions or would like to explore these topics in more detail, don't hesitate to reach out. We're always willing and eager for your engagement. So again, thank you again, and I hope the session has provided you with useful knowledge and inspiration for your own projects. Thank you.